Welcome back. Another week of studying data compression. We are going through EE 274 by Stanford, Professor Tashi Wiseman. Course notes. So this week we went over course notes 1.3, 1.4, and covered one lecture of 1.3. This is where the lecture notes from last quarter and the quarter that the course notes were filmed kind of diverged. I also started Claude Shannon's paper on entropy. That is a long paper. I should have, at some point, more of an in-depth review on it. Same thing with the homework 1, which is up next. Finishing or going through Claude Shannon's paper, and then 1.4's lecture and 1.5 lecture, kind of up to there, and that's what we'll cover for this week. The total hours studied was less than what I had wanted. We had 1 hour on Thursday, 1 hour on Friday, 3 hours on Sunday or Saturday, 4 hours on Sunday, and for a total of 9 hours studied. This time we don't make a mistake on our math. I kind of got preoccupied reading a book. John Green writes fantastic novels. Turtles All the Way Down was the book, if you are interested. So now that we got through all of the summary stuff and what we did, now let's get into kind of the meat. So you'll notice that 1.3 and 1.4 here are mixed. So it goes Kraft inequality, entropy, and then the fundamental limit on lossless compression. And this is just kind of the summary here. We are missing a parentheses. So I'm gonna just do that. I'm really on it there. So Kraft's inequality, what does it mean? So Kraft's inequality is kind of showing that the code words on the leaves of the binary tree are related to the prefix codes, which are related to the length that satisfy the inequality. And so if we're given a prefix code with lengths L1, L2 to LK, it will satisfy this inequality such that the summation of the lengths of the codes will be less than 1. And then conversely, we'll have the length of the codes that are greater than 1, greater than or equal to 1, will satisfy the same inequality, and there will exist a prefix code with lengths L1, L2. So the proof that we start with is the converse, which is Shannon code construction. So kind of a reminder from last time is with Shannon codes is that you're given like A, B, C, and D, and then you're given the probability distribution, and then you are given the code lengths, and then you can use the prefix. You can then use the prefix tree to go down A, B, and then you go down, and then you go down again, or maybe you go down one more, right? And so you'll see that depending on the code construction, this is usually not optimal, and usually to determine if it's optimal, it will actually be the equality of this to be optimal code. So what you can use Kraft's inequality for is finding if you have a set of prefix codes, and then if you want to see if you have an optimal prefix code set, you can use Kraft's inequality as being a Kraft's equality. So the forward of this will be the L max to L1. So you have L1, L max. The L max is the total depth and the total amount of actual nodes in the binary tree, and then that is the total amount of actual theoretical nodes. Now you're not going to fill that binary tree because the descendants don't actually overlap by the definition of a prefix code. So like for instance, I'm not going to go to A, and like I'm not going to put one further down in the depth. So I'm only going to have so many, even though that the tree could be filled up further. So you'll have this being the total sum of the nodes, L max minus Li, which will definitely be less than 2 to the L max. So like I mentioned before, Kraft's inequality will show if a set can have prefix codes, and then Kraft's equality will show that we have found the optimal codes. That was the first half of the lecture. There was a quiz that went inside of it. Granted that I'm self-studying this, I did not do the quiz. I did go through some of the questions, and the questions that I knew without having the answers. So I'd see the answers during that portion. So I didn't do it in a quiz. But that being said, the second half went over a lot of other things, primarily entropy. And so what does entropy mean is like the uncertainty and randomness, i.e. Our upload schedule. So if we only uploaded on Monday, you'd only see uploads. You'd only have that one probability distribution. But because we're uploading this on, I believe, Wednesday or Thursday, now we've introduced some uncertainty into our upload schedule. So that's kind of what it means. The amount of info contained, and more importantly to our context of data compression, is how much we can actually compress. When there's only one code, you can compress a lot because you can just have A be 0. But if there's an actual probability there, we can't compress as much. So it'll be our fundamental limit is entropy. Like we can only go as much as what we calculate for entropy. And so what is entropy? So like given a set of elements and a set of probability distributions, then we can say that the entropy will be the summation of the probability of I, log base 2. That's just because a bit is 0 and 1. If we had instead of binary, we're using ternary, we can go 1 over, like we can do log base 3 here, but because we're using binary, it's in bits, so it'd be log base 2, 1 over p of I, bits, and that would be the entropy, or like the limit that we can compress up to. Some features of entropy is that let x go to, like the set of x be equal to k, then it will be between 0 and entropy will be between 0 and the log base 2 of k, not higher than that. The other big item here, and there's proof that goes along with it in the lecture, is that there is joint entropy. So if I have two independent variables, x1 and x2, the entropy of that will be, or if I have two independent sets, the entropy will be h of x1 plus the entropy of h of x2. So I can use those in joint. There's also relative and K and L divergence. This part was a little bit more confusing to me as the lecture goes on, and trying to make this into a summary video. The important part here is this. If we now have two probability distributions, P and Q. And so you'll see it's very similar to the entropy equation, but that's the divergence. Granted, these are not symmetric, so P and Q here do matter, the ordering. So if I flip them, it would be QI log to PI, or QI over PI. And those are not symmetric. That is one big thing. The big things about the results of lossless compression are that for all prefix codes, we will be greater than entropy. So for all prefix codes, we'll be above that. And then if we can achieve entropy, that is the best that we can do. So we'll be always above entropy. When we create prefix codes, to get the optimal codes, we will be at entropy. That's as far as I got on the understanding and everything there. If you like these progress update videos, please feel free to like the video and subscribe. We have hit 8 subscribers as of this recording. I would like to share more of the good news of data compression. So until next week, I'll see you around. Bye.